Alright guys, so we're gonna do the hydroxy compound for the last lesson. Okay, so for hydroxy compound, right, is basically divided up into two major groups, which is one of which is alcohol, and the other group, right, is what we call the phenol, where we had the OH directly bonded to the benzene ring itself. Okay, let's take a look at how do we actually classify the alcohol. Okay, classification of alcohol is actually important for our syllabus, right? So primary alcohol, the OH is bonded to the C, which have at least two other H bonded to it. All right, at least two other H. Secondary alcohol is bonded to C that has only one H bonded to it. And tertiary alcohol is bonded to a C that has no H bonded to it. Okay, all this actually affects the chemical properties of the functional group, so it's important for us to state the type of alcohol that we're dealing with, right? Physical property wise, alcohol have a boiling point that are much higher due to hydrogen bonding. Okay, solubility wise, they are soluble because they can form hydrogen bond. But as the carbon chain gets longer, right, then the solubility also actually decreases. Okay, acidity wise, alcohols are able to donate H plus, but they are very weak acid. All right, so such that they are actually neutral. All right, and they do not have an effect on litmus paper. So get this, they have acidic H, but they are neutral. Okay, so if you look at this equation, right, you would remember that the strength of an acid actually depends on the availability of the H plus, right? Being able to donate a H plus. Or you can talk about the stability of the anion. All right. So basically, how willing it is to dissociate, all right, and give out the H plus and to become an anion. All right. So for a case of alcohol, the R group, right, intensify the negative charge. All right. So it donates electron to a oxygen atom that's already negative. All right. So this destabilizes the whole anion. So the whole equilibrium tends to the left. All right. So means that the alcohol group doesn't want to dissociate normally. Okay. So here we have all our reactions. We will be looking at them in detail. All right. So the first reaction that we're going to look at is the reaction with sodium metal. All right. So you recall alcohol, even though they're neutral, right, they have actually an acidic H, meaning the OH bond actually can be broken by like things like Na and potassium. Right. These guys are very reactive, so they will abstract the H in order to have a reaction. All right. And then the H that is removed actually forms hydrogen gas. Okay, so some students like to use this as a distinguishing test for alcohol, but I personally find that it's not that good a distinguishing test because it's rather dangerous. All right, because you know sodium is very reactive. Okay, so the reaction of carboxylic acid with your alcohol is a very common reaction which forms your ester in the presence of concentrated sulfuric acid. Right? You kind of learn this reaction, if I'm not wrong, in your secondary 4 or even secondary 3. Okay, so of course your acyl chloride will also react with alcohol because acyl chloride is in fact much more reactive, all right, compared to carboxylic acid. Okay, so this reaction proceeds readily at RTP instead of needing a catalyst. So that actually tells you how reactive the acyl chloride is. And this second reaction is actually irreversible. Compared to the first one, where you use carboxylic acid, it is actually reversible. Next up, we look at the Combustion, I think you all have done it like since secondary school, so not gonna go through it again. Okay, so now this is the part where the properties of primary, secondary, and tertiary actually makes a difference. All right, so the primary alcohol, when you oxidize it, right, it will be oxidized to carboxylic acid. For secondary alcohol, it stops at ketone. For tertiary alcohol, you cannot actually oxidize tertiary alcohol. Okay, so the reagent is manganate or dichromate with heat. Okay, observation: purple KMnO4 decolorize, or orange dichromate turns green. Okay, there's another type of oxidation, which is what we call controlled oxidation. So what we do is we heat the alcohol with distillation, and basically that will allow us to distill off the aldehyde before it is turned to a carboxylic acid. All right, so this is what we call controlled oxidation. Okay, so this reaction corridor is the one which I really like a lot, and it's very useful for us to toggle between primary alcohol, aldehyde, and carboxylic acid. All right, so take note of the reagents and the condition. It's still here. Okay, so if you are using manganate, right, even if you distill, you still will not get the aldehyde because manganate is too strong an oxidizing agent. Okay, so this setup for distillation is just for your information. So the aldehyde would actually vaporize and condense out here, all right, so that you can stop it from proceeding to be oxidized to carboxylic acid. Okay, so some special cases for you to take note. For methanol, right, if you use dichromate, you basically form methanoic acid. If you use KMnO4, you will just oxidize all the way to carbon dioxide. Okay, then for ethane 1,2-diol, right, if you oxidize it using dichromate, you will form ethane dioic acid. But if you use KMnO4, you will go all the way to carbon dioxide. Okay, next up we have a triiodomethane reaction, which is what we call iodoform test. All right, so you have iodine in basic solution with heat, and then if the compound, right, has a carbon that is bonded to a methyl group, a OH group, and a H, you basically will get a yellow PPT of CHI3. All right, so this is what we call a special structure. And I think it'd be great if you can remember the reaction itself. All right, the equation. Okay, so just showing you all the steps that we have to get the eventual product. Please take note, you will need to know all this intermediate, all right? All this intermediate. If they should test you on whether these compounds will form the CHI3, your answer should be yes. Okay, so for the chemical test for alcohol, right, you can use PCl5, all right, which will give you white fumes of HCl. You can also let it undergo oxidation and then add in sodium carbonate to test whether acid has been formed. All right. Okay, so these are the three ways you can distinguish primary, secondary, and tertiary. Triiodoform is only for a special structure. If you have special structure, then yes, you can use triiodoform test to test to distinguish between your two compounds. Okay, second part of the lesson, we're going to be talking on phenol. Phenol is a weak acid. So actually, any question that tells you it is a weak acid, right, you got to suspect phenol, right? But being a weak acid, phenol does not react with sodium carbonate or sodium hydrogen carbonate to give carbon dioxide. All right, so that also is quite telling about the strength of the acid in phenol. Okay, we can distinguish phenol from carboxylic acid with sodium carbonate. Okay, so we will need to know how to describe the relative acidity of phenol, water, and ethanol. Excuse me. All right, so you have your table which explains the relative acidity of phenol, water, and ethanol. All right, so when you look at ethanol, right, the electron donating group actually causes the intensity of the negative charge on the O atom, right, to intensify. All right, so this destabilizes the alkoxide, which is this thing over here. Okay, so equilibrium tends to the left. All right, so that makes it least acidic. Okay, then we look at phenol, right? The negative charge is dispersed into the ring, so it actually causes the phenoxide ion to be more stabilized, so therefore the equilibrium will shift to the right, giving us more H+. That's why it is most acidic among the three. So now we look at the effect of substituent on the acid strength of the phenol. So if let's say you have an R group on the ring, right, it donates electron. This destabilizes the phenoxide, so it decreases the acid strength. But if you have an electron withdrawing group, all right, that withdraws electron density from the ring, then that will actually stabilize the phenoxide, okay, making it more acidic. Okay, reactions of phenol, basically you can have some on the OH bond and some on the ring itself. Okay, the question, why does phenol require milder condition, right, for electrophilic sub on the ring, is because the lone pair delocalize in the ring and increase the electron density, thus activating the ring and making it more susceptible to electrophilic attack. Okay, so this is just a summary. So phenol also will react with a reactive metal. So this reaction proceeds at RTP and will give you a hydrogen gas. Okay, like I said before, I don't think this is really one of the best distinguishing tests. If you have a choice, choose something else. All right, so phenol will react with base, but not with sodium carbonate, in case you are wondering. Okay, so it undergoes neutralization. Alcohol also react with acyl chloride, which is an acid derivative. Okay, remember, phenol can only react with acyl chloride to form ester. Okay, it cannot react with carboxylic acid. All right, it's not strong enough. Okay, so if you want to make phenol a better nucleophile, you can neutralize it with NaOH. Then you get the phenoxide, which is a stronger nucleophile. Okay, so if you remember a benzene ring, right? If you want to add in a nitro group, you have to use corn sulfuric, corn nitric plus heat, right, to make it happen. But here, because the ring is already activated, you just need to use a dilute nitric acid. All right, then you will have a 2 and 4 substitution. Okay, if you use concentrated nitric acid, right, at RTP, basically you already get tri-substitution. It is that activated, right? So reaction with halogen. So basically, because it's activated, right, you just add the halogen in CCl4, you get 2,4 substitution. And if you put it in aqueous solution, you will get 2,4,6 tri-substitution. Okay, please take note of your observation. Okay, one common question that student ask me, right, how come the bromine, right, when it is more concentrated, so-called in liquid form, you only get mono sub. But aqueous form, right, you get tri-sub. Like, doesn't make sense, right? But this can be explained by the fact that in aqueous medium, right, the phenol can exist as phenoxide, right? So phenoxide, the lone pair can delocalize in the ring and activating the ring much more. All right, so that's why it undergoes tri-substitution. Chemical tests, you can add neutral FeCl3 and giving you a violet complex. Okay, so why must it be neutral, right? In acidic solution, you cannot generate phenoxide. All right, in basic solution, iron hydroxide will be precipitated out, so it will screw up your observation. All right. Okay, you can also add aqueous bromine just to see the decolorization and the formation of white PPT. Okay, note that this test will give the same result with phenylamine. Okay, remember in our alkenes, right, we have looked at how you can add water across the CC double bond. All right, so much of this is actually recap work. Okay, for your carbonyl, they can also undergo reduction to form back your alcohol. Okay, carbonyl will be the next chapter that we're going to go to. Carboxylic acid can also undergo reduction to form your primary alcohol. Okay, take note that only lithium aluminum hydride is strong enough to reduce carboxylic acid. Okay, so this is the quick check for you. Sodium boron hydride, it will only act on a carbonyl group to reduce it. It will not touch any other group. All right, so just take note of that. All right, so now we move on to the MCQs. So which of the following product is formed when Y is distilled with dichromate? Okay, so when you use oxidation, controlled oxidation, right? So you basically will reduce, will oxidize this to your aldehyde, and of course your secondary alcohols will be oxidized to ketones. All right, tertiary alcohol will not be oxidized. Okay, so your answer is C. 2, right? Which of the statement is correct? You can undergo oxidation with hot alkaline KMO4. The oxidation is actually here. All right, side chain. Okay, so same thing here. Okay, side chain of the arenes. Okay, question 3, what are the types of reaction involved? All 3 types. Okay, all 3 types are present. Okay, so the first step is free radical sub. Okay, second step, you basically undergo your dehydration and nucleophilic sub at the same time. All right, because remember there's a H here. There's a H here, so you can actually take out the HBr and then substitute the Br with OH. Okay, question 4. If SN1 takes place more rapidly in polar solvent, right? Which solvent can we use? So just choose the polar solvent. That's the answer already. Okay, question 5. Which compound does not form precipitate? Compound X will not form the precipitate because CF bond is very, very strong. Will not form. Okay, it cannot be substituted out. Okay, which one forms the fastest? Which of course is this acyl bromide. It will form the fastest. Okay, so the color is pale cream. AgBr. Okay, which species could be an intermediate? This one is basically just your nucleophilic sub. Right, so you will get concentrated. So the only two plausible one is actually your B and C. Yeah? A and B doesn't really make sense. All right, so we need to consider the BR, right? Whether it is like a more prone to undergo oxidation or more not oxidation, sorry, is it more prone to undergo SN1 or SN2? Okay, the answer is it will undergo SN1 because the negative charge, right, can be dispersed into the ring. All right, so because this C, right, is actually your sp2 hybridized, so the negative charge can be dispersed by the ring. Okay, so that's why it's more stabilized. It will be more favorably formed. Okay, 7 molecular formula is C5H12O. What is the identity? So it has a special structure. It can be dehydrated to form 2 alkenes only. So if you draw out your structure, right? H. So it has a special structure right here. And then you can form a double bond here or here. Okay, and that's it. Okay, question 8. How many moles of silver chloride will be precipitated out? The only ones that can be precipitated out is this and this chloride. Okay, this chlorine, right, is actually directly bonded to a double bond, so it will also form a partial double bond character, same as the chlorine bonded here. All right, this is actually a concept taught in halogenal alkane. Okay, question 9. The following two compounds react with alkaline iodine. So it's triadoform test. What's the ratio of sodium hydroxide used to react with 1 mole of V and 1 mole of W? Okay, so this one you got to remember the chemical equation. Okay, and this one I can't help you. You just have to look at the chemical equation to find out the mole ratio. Okay, last question. So you use ethanolic KOH, you will actually form a double bond here, and form a double bond here. That's it. Okay, so how many isomers? This one there's no cis trans. This one there is cis trans. This one no cis trans. So cis and trans 2 to the power of 1, right? Plus chiral carbon here. Okay, 2 to the power of 2. Okay, and let's see, cis trans 1. Okay, and then there is 2 other alkene which cannot form cis trans. All right, so plus 2. So total is 6. All right, so if you are in doubt, please draw out the isomers to check